Magnetic resonance imaging, or MRI, is a powerful medical imaging technology used to view detailed images or organs and tissues inside the human body. Unlike X-rays or CT scans, MRI does not use ionizing radiation. Instead, it uses strong magnetic fields and radio waves to produce clear and accurate images. MRI machines are especially important in diagnosing conditions involving the brain, spine, joints, and soft tissues, making them an essential tool in modern medicine. So for the MRI process, the hydrogen proton, the first one is spin and magnetism. Hydrogen proton possess an important quantum property known as nuclear spin. Because it is a charged particle in motion, it produces a small localized magnetic field. Each proton can be imagined as a tiny bar magnet within the body. The second one is abundance. Hydrogen is ideal for MRI because it is extremely abundant in the human body, especially in water and fat. This abundance provides the MRI scanner with millions of tiny magnetic sources, enabling strong and detailed signals detection. So for the last one is coil structure. The MRI magnet is designed in a solenoid configuration. Superconducting wires are wound into a large cylindrical coil, forming a tunnel through its center. This structure ensures that the magnetic field produced is strong, uniform, and aligned parallel to the central axis of the scanner. So for the main magnetic field, the primary role of the MRI magnet is to generate the main magnetic field. This magnetic field must be extremely strong and highly uniform throughout the imaging region to produce clear and accurate image. The second one is superconductivity. The magnet coils are constructed using superconducting wires which have zero electrical resistance. When these coils are cooled below a critical temperature, electric resistance disappears, allowing a large electric current to flow continuously without requiring an external power source. The last one is initial state. Under normal conditions, outside the influence of the MRI scanner, hydrogen protons are oriented randomly throughout the body. Their magnetic field cancel each other out, resulting in no overall magnetic signal.
Okay, next we go to magnetic field in MRI scan. This diagram shows magnetic field shading using iron. The dashed line represent magnetic field lines. Without shading, the magnetic field separate freely and is very strong, which we can call an unshading field. The iron plate placed above and below act as a magnetic shield. Iron has high magnetic permeability, so magnetic field lines prefer to pass through the iron instead of air or the human body. As the result, the magnetic field lines are redirected around the protected region, not blocked. This reduces the magnetic field strength inside the shield area about 5 Gauss, which is a much safer. Therefore, magnetic shield work by diverting magnetic field line, not eliminating them. This principle is commonly used in MRI machine and electronic equipment protection. Next, we go to physics principle, magnetism. Proton alignment. Protons have positive charge and spin, so they act like teeny bar magnet. Without an external magnetic field, proton direction are random. When placed in a strong magnetic field, B0, most protons align parallel to the field and low energy. A smaller number align anti-parallel high energy. This creates a net magnetization in the direction of the magnetic field. Next, proton precession. Protons do not point straight along the magnetic field. Instead, they process wobble around the direction of the field. This motion is similar to the spinning top under gravity. The last one is a Lamont frequency. The speed of precession is called the Lamont frequency. It depends on the strength of the magnetic field. Next, I will explain more about the Lamont frequency. Lamont frequency is the frequency at which proton persist or wobble around an external magnetic field. The formula is shown here. Fl equals to gamma over 2 pi B0. In this equation, gamma is the gyromagnetic ratio, which is a constant for proton, and B naught is the strength of the magnetic field. This means the low frequency is directly proportional to the magnetic field strength. A strong magnetic field causes the proton to precede faster. The diagram on the right shows how the proton precesses in a circular motion around the direction of the magnetic field.
Generation of radio frequency. RF coil, the hardware. Radio frequency RF coil acts as the MRI machine antenna system, responsible for transmitting the oscillating magnetic pulse that excites proton and subsequently receiving the faint signal emitted by the body to generate an image. First, the pulse, electricity. The machine sends a burst of alternating electric current through the coil. This creates an oscillating magnetic field called the B1 field. The B1 field is oscillating, moving back and forth at a specific speed and applied perpendicularly at 90 degrees to the main magnetic field. Second, physics principle, resonance. MRI machine relies on the principle of resonance to ensure it will only affect the specific proton we want to image. For the proton to absorb energy, the RF pulse frequency must watch the Lambda frequency exactly. If the frequency match, energy is transferred, resonant. If they do not match, the proton ignores the pulse. 3. The excitation phase. Once resonance is achieved, the proton undergoes excitation, where the RF pulse is turned on. The low energy proton, those facing up, catch the wave and absorb the energy. Before the pulse, protons are spinning at different positions out of phase. The RF pulse forces them to spin together in perfect synchronization in phase. Because of this extra energy of synchronization, the net magnetization vector NMV, which was standing straight up, tips over 90 degrees. The magnetic vector is now spinning in the transverse plane flat. This is the only position where the MRI machine can actually read the signal. Signal reception and image creation. Signal generation, relaxation phase. After the RF radio frequency pulse is turned off, the excited protons slowly return to their original alignment with the strong magnetic field. This process is called relaxation, T1 and T2 relaxation. As the proton relax, they release the absorbed energy in the form of tiny radio signal. The MRI scanners receive coil detect the signals. Difference in relaxation time between tissue create contrast in MRI image. Special localization, gradient coil. MRI uses gradient coil that rapidly switch electric current on and off. These coils slightly alter the magnetic field strength in specific direction, X, Y, and Z. Because magnetic field strength determines the Lambda frequency, changing the field causes proton in a different location to persist at different frequencies. The scanner uses this frequency difference to determine where the signal comes from. This allows the system to assign exact position to each signal, forming a detailed 2D or 3D image. Conclusion. Magnetic resonance imaging or MRI is a powerful medical imaging technology used to view detailed image of organs and tissue inside the human body. Unlike X-ray or CT scan, MRI does not use ionizing radiation. Instead, it uses strong magnetic field and radio waves to produce clear and accurate image. MRI machines are especially important in diagnosing conditions involving the brain, spine, joint, and soft tissues, making them an essential tool in modern medicine.